Okay, we're going to look at exponential growth and decay functions, but before we do that, we have one final financial equation to look at, and that is what they call an annuity. Now, annuities also can be used for certain kinds of insurance instruments. They can be a fund that pays somebody throughout their lifetime when they retire. So I don't think this word is unique, but annuity can be used for an equation like this where instead of just putting in an initial principal and walking away and seeing how it grows over time like we looked at before, you put in monthly, quarterly, or periodic payments over time. So this is the equation. It's pretty similar to what we've already looked at. A couple of minor changes here. First, the amount, that's the same, although it can be referred to as the accumulated or future value of the annuity. Just different names for the same thing. It's how much you've got. Then a little something different. In the previous equation, we had a rate, an interest rate, shall we say, an annual rate, and then we had the number of compounds per year, and we had the time in years that the investment would grow. You don't see any of those in this equation here, but they are part of the problems. What they are, though, is when you collect this information, the R and the N represent those. So the capital R is calculated as rate over number of compounds, and then the capital N, which shows up here, has the number of compounds times the number of years for the annuity. So these values are included in the equation, you just don't see them because they're entered like this. Finally, P is your periodic payment. So if it's quarterly, you're going to do 4 payments a year, monthly, 12 payments a year, and so on. So that's going to match the compounds also. So P payments, N payments a year. Now, one other thing about this, if you solve this for P, in other words, multiply both sides by R, so I'd have AR, and then divide both sides by this quantity here, you're going to wind up with this. And they give it a different name and all that, but look, it's exactly the same thing as this. It's just solved for P. It's still the payment that you're going to need to make, but when it's in this format, it's often referred to as a sinking fund, and pretty much just means here would be how much do I got to sink into this account or put into this account to grow to this much money at these rates and compounds, basically. So here P is referred to as a sinking fund. Here P is referred to as your periodic payment. They're exactly the same thing. It's just two different ways of looking at it. These solve exactly the same way that the other financial equations did. So I'll just do one example so we can see how this works. And we can kind of get an idea of, maybe picking this one or this one over the other one, although it doesn't matter. All right, so here's our problem here. So we have a person who wants to save $4,700 in 4 years at this rate, 8.5%, and it's compounded quarterly. So how much do they need to invest each quarter? Well, since that's how much does their payment have to be, we could use this equation, but then we got to solve it anyways to get P by itself. So let's go ahead and use this one. So P equals, and what I would like to do is save $4,700. That would be my amount I would like. And I want to do that in 4 years at 8.5%. But again, you don't see years, you don't see the quarterly compound or the rate in this formula. So we got to go do this. So what I have here is I want my time to be 4 years. I'm just getting it right out of the problem here. I want my rate, and again, be careful here, that's a small r for the rate. Big R is what we're going to calculate later, and that's what's in the formula. 8.5, so convert to a decimal, 0.85. And then finally, we're compounding quarterly, so that's 4 a year. And again, that's a small n. We're going to calculate big N, and that's what's in the formula, not the small n. Okay, so R equals R over N. So big R equals little r over N, which is 4. And if I divide that out, I should get this. So now I can put R in here. Okay. So we can put that here. 0.02125. And down here I have 1 plus R again. Raised to the n power, but I don't know what that is yet, so let's do that one next. N equals compound small n times time, small t. That's 16, so that goes here, and minus 1. And that's it. So just use your calculator. These are easy to solve. Let's just go down here. If I multiply these two together, and then if I add this, that's 1.02125. I enter that in my calculator with this key here. Enter this, hit this, and then enter 16 for the exponent, hit the equal sign. I'm going to get this. The further out you can go in decimal places, the more accurate these are going to be, because you're going to get into estimates sometimes. So I like to go 4 or 5 places. And then we still have the minus 1. If I subtract this, I just have 0.39995. Divide that into this, and P equals 249.72, and that's dollars because that's what my payment's going to be every quarter. Okay. There are some good examples in the book on these problems if you want to look at more of those, but basically this is a good example of everything. Okay. Let's move on to growth and decay. And what do we have here? Okay. The first thing you'll notice is the equation's really actually the same. QT equals Q0 e to the RT. Q0 is your initial population, starting population. T is the time that goes by, lapse time. Q of T is the population at that time. And then R is the rate. It's just a rate. And when you put the rate into the equation, if you decide it's a growth equation, like a population growing over time, or you're going to use a positive exponent. And again, e to a positive exponent goes up. If you remember the curve, that's growth. If it's a decay, like radioactive decay, that kind of thing, population dying off at a certain rate, then you're going to want to use a negative exponent. So that's the only difference between the two equations. Okay, so let's look at a couple problems here. Let me get down here. Okay. A certain bacteria doubles in population every 12 hours. That's growth. Okay, so we're here. Find the growth rate and then estimate the time for the population to go from 1,000 to 200,000 bacteria. Right. We have to find the growth rate first. So what do we have here? Q of t. So what do we want to do there? Well, we aren't specifically given Q of t or Q0 for that matter. So what am I going to plug in here? Well, let's look at what it says. Q of t is going to equal twice the initial population in 12 hours. So now I have three things I can plug in and solve for R. And the way we plug in is this. Q of t equals 2 times Q0. So that goes here. Q0 is here. E to the... So again, let's look at that. If I start at Q0, it doubles in 12 hours. So that's how these things set up. They're all very similar to this. All right, and the beauty here is they cancel, so now I have one variable so I can solve. And again, how do I get rid of a variable and an exponent? Since that's base E, I want to use natural log. So natural log of both sides. And then the E and the natural log will cancel. And then finally, if I divide both sides by 12, take the natural log, divide 12 into that, I'm going to come out with R equals 0.058, which is what I'll use in part 2. And if I'm reporting what the growth rate is, then I'm going to report R equal 5.8%. Okay, next part. Now I have everything I need I can just plug in. I want a sample at time t to be 200,000. I'm starting at 1,000, that's my starting pop. My rate is 0.058. And I'm trying to figure out what the time would be to get me from here to here, so t's unknown. So again, I need to isolate this E value so I can take the natural log and cancel it out. So I need to divide both sides by 1,000. So that's gone. And I get rid of 3 zeros here. So what do I have here? 200 equals E to the 0.058t. Take the natural log of both sides. Let's go over here. ln of 200. Natural log and the E will cancel, so I get this. Again, if I divide both sides by 0.058, take the natural log of 200, divide by 0.058, and you're going to get t equals 91.4. And if you go back and look at the problem, we're talking about hours. So that's how you do a growth problem. We'll look at a decay problem next, basically the same thing, but this one's got a bit of a twist to it. The reason here, you'll see in a minute, this is a radioactive half-life problem. So we got a situation here. First, some background. Carbon-14, it's a radioactive substance. It's on all living things. It has a half-life, but as long as things are living, they continue to absorb this stuff. And what happens is when a person, a tree, an animal, whatever, when they die, carbon-14 is no longer absorbed into that life form. So it starts decaying. And you can use that to approximate when this thing died. So roughly how old is it when you found it? So that's what's going on here. We need to know what the half-life is. It's every 5730 years you have half of what you started with, so it takes a long time for this stuff to decay. We found a mummy and it had 45% of its carbon-14 remaining. You can do tests for that. So the question is, roughly how old's a mummy? Okay, here's the problem. I have no idea. I'm missing data here. 45% of its carbon is remaining, so at least I know the populations. If I started with a certain amount of carbon-14, then QT would equal 45% of that starting amount. So I have QT and I have Q0. But the problem is I don't have a rate or a time. They're not here. You can't solve an equation with two variables. You have to have one variable to solve it. Okay, but we can do it because for radioactive decay, we have this half-life formula here. What you do is you put the half-life here and you divide ln2 by the half-life, and that gives you the rate for that radioactive decay. So that's how you get the rate. Then we'll be able to solve this because we'll only have t is missing. So what is the rate? Well, rate equals ln2 over the half-life is 5730. Again, ln2 on your calculator, divided by 5730, and you're going to come up with a pretty small number here. So now we have a rate. So now all we do is plug in to this equation. Now notice here, that's just a rate, it's positive, but the equation says make the exponent negative. So what we're doing here is for Q of t, I want 45% of my starting. So that's Q of t, but I started with all of that, and then I have e to the negative, and now my rate is here. And I'm solving for t. And again, I think this is starting to look real familiar. Isolate the e term, take the natural log of both sides, and it cancels it out, and you get the exponent down where you can work with it. So those cancel. Take the natural log of both sides. And that cancels out the e then. Divide both sides by -0. And the good news here is the natural log of 0.45 is also a negative, so we're going to get a positive answer for t, which is what we want. If you do this, you're going to end up with approximately 6599, and we're talking years here. So our mummy is approximately 6,600 years old.